So again, this case we've been given the Taylor series in the sigma notation form again, so we don't need to generate our own Taylor series sigma notation. So we're just going to start with that. So we're going to start with our ratio test. Okay, so then we're going to set up a ratio test, the limit, as n approaches infinity. It's going to be -1 to the n plus 1, x to the 2n plus 3, because when we substitute n plus 1 into here, it's going to be 2 times n plus 1 plus 1. Okay, and then the same goes for that denominator. When we substitute the n plus 1, we're going to end up with 2n plus 3. Okay, so there's our ratio, and we're going to do this over -1 to the power n, x to the 2n plus 1 over 2n plus 1. Okay, just clean that up a bit. Zoom in. So it's going to be 2n here, and that's 2n plus 1. And we want to know where that ratio test is going to give us a ratio less than 1. And again, if you recall, the reason why we do this is because we want to see if this behaves like a geometric series at large values of n. If the ratio is less than 1, then we know that the multiplier, the term by term multiplier, is a ratio less than 1, which then will make it behave like an infinite geometric series, which is convergent. Okay, so let's do the algebra part here. Okay, so then we have -1. Okay, this is going to be x to the power 2n plus 3 divided by 2n plus 1, x to the power 2. And then for the sequence part of it, it's going to end up being 2n plus 1 in the numerator, 2n plus 3 in the denominator, and we're going to let the limit of that go to 0. Okay, well 2n plus 1 over 2n plus 3 as the limit as it goes to 0, that's going to end up just being 1. Okay, so then when we put that in, we can evaluate the limit now. Okay, so the absolute value of x squared is less than 1. Okay, so this one here, we can, again, the center is, this one's got a center at 0, and we can kind of see that, yeah, since it's equal to 1 when we square root both sides, the radius is still going to be 1. So our interval is -1 to 1. Okay, then comes our test. We need to test that interval. Okay, so we're going to test our interval over here. So our test is going to be for x equals -1. When we test x equals -1, let's make sure that's more clear. X equals -1. When I plug that into my sigma notation, I end up with -1 to the power n. This is going to be -1 to the 2n plus 1. Okay, so that becomes 3n plus 1. And then what we're going to end up with is, this is over 2n plus 1. Okay, so 3n plus 1 means that it's going to, if n is 1, we're going to get 3n plus 1, which is 4. With n is 2, okay, we're going to end up with 6n plus 1, which is 7. So it's going to go from 4 to 7, even to odd. This is going to alternate, and it's going to be an alternating harmonic series. It's going to behave like an alternating harmonic series because that term in the denominator is a linear term. So that means then that it's going to behave like a harmonic series. So this is convergent, okay, because it alternates. Okay, and in fact, we didn't even have to worry about the fact that being harmonic. We just know that that goes to 0. If it alternates, there's an alternating series theorem that says that would be convergent. Okay, so I've got convergence here for that. So I'm going to include that as my endpoint. Test the other endpoint. Okay, we're going to test x equals +1. Okay, in this case, what are we going to end up with? We're going to end up with -1 to the n, and this is going to be +1 to the 2n plus 1. Okay, so this is going to be an alternating series because that's just going to be 1. And now that is harmonic. It's a harmonic series. Same thing as before. We are going to say that this is convergent as well because essentially it's the same series as we got when we tested the other endpoint. Okay, so it's convergent. So on the right-hand side being convergent, okay, for that we can then change the right-hand endpoint to equal to 1. Okay, so this is now my interval of convergence.